So we're on to the back page and solving polynomial functions for their roots. These first few examples and tomorrow that you're going to see are all going to be factorable polynomials. So we're going to apply our basic factoring techniques. So if you look up here, these are the basic factoring methods that you're going to want to look to try to employ. Even when they're unfactorable later in the week, you're still going to look to try to factor any GCFs if there are any that exist in the beginning. That's what makes your life simpler when you're trying to solve these. So for all of these, solving a polynomial is just like solving a quadratic like we did earlier in the year. So you basically want to set it equal to 0 to find the roots, or where it crosses the x-axis, or the zeros of the function. So setting the function equal to 0 is isolating where those occurrences happen. So over here, we'd want to move this over. So we're going to start off with 3y to the fourth minus 6y cubed plus 3y squared, and that's equal to 0. So that's like our starting point. Once we have that, we can notice that there's a common GCF, greatest common factor of 3y squared. That's in every term. So if we take that out, we get 3y squared times, this becomes y squared minus 2y plus 1 is equal to 0. So here's where we can employ the same concepts as we would with quadratics with making a t-chart. Like if this factor times that factor has a product of 0, that means that either one or both of these have to be 0. So we can set each one equal to 0 and set up our little t-chart. So we go like this. Basically, we have 3y squared is equal to 0. That's one factor. And the other one is y squared minus 2y plus 1 is equal to 0. So this one's not too hard to solve, because if you divide by 3, you get back to y squared equals 0. So y is equal to basically plus or minus the square root of 0. Well, plus square root of 0 minus square root of 0 are the same answer. That's just y equals 0, but it's kind of like that thing happening twice. There's like two roots there for that particular value. So remember back to last week with multiplicity of roots, that would indicate that at 0, now they're using y as the variable, but normally this would be like f of x, or this would be an x variable. This is the input variable, even though it's a y. So it represents like an x. So this would represent a value of x, or in this case y, having a double root at that spot. So I'll show what the picture might look like based on that happening. Over here, if we factor this out, this is also going to factor into y minus 1 times y minus 1 equals 0. It's kind of like a t-chart within a t-chart. So here you have y minus 1 equals 0, y minus 1 equals 0 again. You get y equals 1, and you get y equals 1. You get a double root again. It's kind of the same root twice again, just like this was twice. So what that means in the big picture is if we were to sketch this at 0, where there's a root, and 1, where there's also a root, the graph is going to bounce off those spots, right? And if you notice in the very beginning, see how this is the polynomials in standard form? The leading coefficient is positive, and it's an even degree. So going back to last week, that means the function should travel in the same direction at both ends, and it better be face up, traveling off into the first quadrant in the long run. It's going to look something like that. But remember, since this is a double root here, this is going to kind of bounce off, and then it's going to come back towards this root. But again, this is a double root also, since there were two of them at that spot. So this is going to bounce off again, and it's going to go up again towards the left. So notice that it's going off in the same direction like an even degree should, and it's positive leading coefficient, so it's going to go up to the right. This would be what the picture might look like if you were to graph that function out using like f of x format, where the y would be like an x. Remember, these variables could be any letters, doesn't really matter. Okay. Moving on to the second one, it's actually probably a little bit simpler because it's factoring by grouping. So if you remember that technique, it's like you're pairing them off and just finding two GCFs. So in this case, you're going to have a GCF of n squared. So you have n squared times n plus 2. And then if it's going to work by grouping, this factor should be the same over here. So see how these have a common factor of negative 9? If you take out a negative 9, you're left with n plus 2 again, negative 9n minus 18. So both of those factors come out, and then this becomes your GCF when you factor by grouping. So we have an n plus 2 times the coefficients, this and this, are what's left over. So there's your factoring by grouping. So when we have that, we do the same thing we did before. You can do a little t-chart. This factor over here is set equal to 0, and this factor over here is set equal to 0. This is going to yield a root of negative 2. This is going to factor into n plus 3 and n minus 3. So you're going to get two roots. One is going to be negative 3, and one is going to be positive 3. Okay, so we have 1, 2, 3 roots. They're all singular roots. So in this case, if we were to sketch a picture, negative 1, 2, and 3, there's a